Dear children, in the previous session, we have discussed various types of relations. Now, equivalence relation. A relation on a set A is said to be an equivalence relation on A if and only if it is reflexive. That is, every element of A is related to itself, ordered by A element of R, for all A element of A. Second condition is symmetric. That is, A element of ordered by AB element of R implies ordered by BA element of R, for all A and B elements of the set A. And the third condition is transitive. That is, AB element of ordered by AB element of R ordered by BC element of R implies ordered by AC element of R, for all A, B, C element of the set A. If all the three conditions are satisfied, then the relation R is said to be an equivalence relation. Let us have an example. The question is, prove that the relation R on the set of all integers defined by ordered by xy element of R implies and implied by x minus y is divisible by 3 is an equivalence relation. So, to prove it's an equivalence relation, we have to establish the reflexivity, symmetricity and transitivity. Let us do one by one. So, I am taking a reflexivity case first. Reflexive. To prove R is reflexive, I am taking a general element from set, a general integer, arbitrary integer. So, let's. A is an integer, so A element of set. Since A is an integer, what about A minus A? A minus A is equal to 0. A minus A is equal to 0, but 0 is divisible by 3. Yes. Divisible by 3. Now, as per the definition of the relation, x minus y is divisible by 3 means xy element of R. So, A minus A equal to 0 implies AA element of R. So, the relation R is reflexive. Therefore, R is reflexive. So, that part is over. Now, we have to prove it is symmetric. Now, I have to check symmetricity case. Symmetric case. Symmetric means that if A is related to B, then B should be related to A. So, I am taking two elements, A and B, A comma B, and element of set, the two arbitrary integers, and A is related to B, ordered by AB element of R. Now we have to get B is related to A. Now, A related to B implies, as per the definition of the relation, A minus B is divisible by by 3. If A minus B is divisible by 3, then it is clear that B minus A is also divisible by 10. So B minus A divisible by 3 means, as per this condition, BA should be an element of ordered pair BA should be an element of R, which implies that ordered pair BA element of R. So ordered pair AB element of R implies ordered pair BA element of R. Therefore, R is symmetric. R is symmetric. So, reflexivity over, symmetricity is over. Now, we have to prove it is a transit. Next case is transit. Transitive case. So, for the transitivity case, I am taking letter A, B, C with 3 arbitrary integers and A is related to B, that is ordered pair AB element of R, comma, B is related to C. We have to get A is related to C. Now, A related to B implies A related to B implies A minus B is divisible by by 3. A minus B is divisible by 3 means A minus B is a multiple of 3. So, implies A minus B is equal to some 3m, where m is an integer. Where 3m is an integer. I am taking this as equation number 1. Now, the next case is B is related to C. B ordered by BC element of R implies B is related to C implies B minus C is divisible by 3. Automatically B minus C will be a multiple of 3. So directly I am writing B minus C is equal to some multiple of 3. Because B minus C is divisible by 3 means it is a multiple of 3. So it is equal to some 3n from some other integer n. So we are having two equations here, 1 and 2. We just add 1 and 2. We are adding 1 and 2. 1 plus 2 gives. First one is A minus B plus, next is B minus C, and that is equal to 3m plus 3n. Now minus 3 and plus 3. So we are having A minus C is equal to, now let us take 3 outside as a common factor. So 3 in m plus n. 3 into m plus n means it is multiple of 3, therefore divisible by 3. Implies A minus C is divisible by 3 means ordered pair AC, that is A is related to C. That is what we get now. A is related to B, ordered pair AB element of R, comma, ordered pair BC element of R, implies ordered pair AC element of R. So the transitivity is over. Therefore, R is transitive. R is transitive. R is transitive. So R is reflexive, symmetric and transitive, hence R is an equivalence relation. Therefore, hence R is an equivalence relation. Hence we have proved R is an equivalence relation. Now, in this example, we have defined a relation R on the set of integers in such a way that A is related to B or X is related to Y implies X minus Y is divisible by 3, and we have proved that that is an equivalence relation. Now, with the help of this example, I am going to define another thing. What is that? See here. I am clearing all these things. Dear children, we have defined the relation R on the set of all integers. The R is defined in such a way that X is related to Y implies X minus Y is divisible by 3. Okay, that is for the sake of convenience, I am writing here ordered where XY element of R implies, and implied by X minus Y is divisible by 3. This was the relation. This was the relation for us, and put it in a box. So this is the relation. Now, let us say it is a defined set of all integers. Now, under this relation, the elements are related to the set of elements related to 0 under this relation. What are the set of elements related to 0? Let me write the set. This will be equal to the set of elements. Clearly, the relation is an equivalence relation, so it is a reflexive. So 0 should be related to 0. So 0 is an element. I am writing 0. I am writing this as 0. Now, whether 1 is related to 0, if 1 is related to 0, 1 minus 0 should be divisible by 3, so it is not possible. So 1 is not related to 0. Whether 2 is related to 0, 2 minus 0 is not divisible by 3, so it is not related. 2 is not related to 3. Now, what about 3? 3 minus 3 is divisible by 3. So 3 is related to 3. Sorry, 3 is related to 0. 3 minus 0 is 3 is divisible. So it is 3. Now whether 4 is related to 0? No. 4 minus 0 is 4 only. 5 is not related, but 6 is related to 0. So 6 minus 0 is 6 divisible by 3. So 6. Now next is 7 not related, 8 not related, but 9 is related to 0. So it is 9. Except now left side of 0, whether minus 1 is related to 0, minus 1 minus 0 is minus 1 only, negative 1 only, it is not divisible by 3. Negative 2 is not divisible by 3. Negative 3, yes, negative 3 is divisible by 3. So negative 3 is possible. Negative 4 not divisible. Negative 4 is not related to 3. Negative 5 is not related to 3, but negative 6 is related to 3. So negative 6 and etc. It will come this way. So these are the elements related to 0. Let me find the elements related to the elements or integers the elements under this relation related to 1. I'm taking 1. So instead of 5, 1. Since it is an equivalence relation, it is reflexive. So this is when I am writing this set, without any difficulty I can write 1. 1 is related to 1. Whether 2 is related to 1, 2 minus 1 is 1 only, it is not divisible. 3 is related to 1, no, 3 minus 1 is 2, not related. 4 minus 4 is related to 1. Reason? 4 minus 1 is equal to 3, which is divisible by 3. So 4 is related. 5 not related, 6 not related, but 7 is related to 1. So 7. Now left side of 1. Whether 0 related to 1? No. 0 minus 1 is negative 1 only. It is not divisible by 3. Minus 1. Minus 1 minus 1 is minus 2. Negative 2, it is not divisible. Negative 2 minus 1 is negative 3, which is divisible. So negative 2 is possible. Negative 2 is possible. Now, negative 3 not possible. Negative 3 minus 1 is negative 4, not possible. Negative 5. Negative 4. Negative 3 is not possible. Negative 4. Negative 4 minus 1 is negative 5. It is not divisible. But negative 5. Negative 5 minus 1 is negative 6. So, negative 6. Sorry, it is negative 5. Negative 5. Excellent. Now, the third case I am taking. The set of elements, set of integers related to 2. Set of integers related to 2. Of course, 2 is related to 2 as it is reflex. 2 is related to 2. Now, whether 3 is related to 2? Not possible, because 3 minus 2 is 1, it is not divisible. Whether 4 is related to 2? 4 minus 2 is equal to 2, it is not divisible. Whether 5 is related to 2? 5 minus 2 is equal to 3 is divisible. So, it is 5. 5 possible. 6 not possible. 7 not possible. 8. 8 minus 2 is equal to 6. So 8 possible. Excellent. Excellent. Now in the left side of 2. 1. 1 minus 2 is not divisible. Now what about 0? 0 minus 2 is also not divisible. Now what about negative 1? Negative 1 minus 2 is negative 3, so it is divisible. So it is negative. Come on. Now, negative 2 minus negative 2 is negative 4 is not divisible. Negative 3 minus negative 2 is negative 5, which is not divisible. Now, negative 4 minus 2 is negative 6, so it is divisible. So negative 6. I'm taking a little time. Why? Because now we got 3 sets of integers which are related to, first set is related to 0, second set is related to 1, and the third set is related to 2. May I take another set also? The set of elements related to 3. Set of integers related to 3. That is, now clearly we can write 3 as it is an equivalence relation reflex. 3 is related to 3. 4 is related to 3? Not correct. 5 related to 3? Not possible. But 6 is possible. So 6. 7 not related to 3. 8 not related to 3. But 9 is related to 3. Now left side of 3. 2 not related to 3. 1 not related to 3 because 1 minus 3 is 2 only. Not possible. 0 is related to 3 because 0 minus 3 is negative 3. So 0 possible. Negative 1 not possible. Negative 2 not possible. Negative 3 is possible. So negative 3. Negative 6. We are getting this. Dear children, check this set and this set. This set. Here also 0, 3, 6, 9, etc. And what about here? Here also the same. So if you continue like that, you will get the same sets only. Now what we got? Whether any common here in this set, here any common? No, there is no element is in common. So these 3 sets what we got right now are mutually disjoint sets. They are disjoint, pairwise disjoint. Of course, what will be the union of these 3 sets? When we take the union of these 3 sets, we will get the set of all integers. So, what exercise we have done here? We have taken one set of all integers and defined a relation R, and that R is an equivalence relation. Now, with the help of that R, I have divided this total integers into 3 disjoint sets. And this process is known as the partition of the set. And each set, this set of all related to 0, set of all related to 1, set of all related to 2 are called equivalence classes. So, equivalence class corresponding to 0 is this set and it is denoted by this way. This is the equivalence class corresponding to 0. Now, this is the set of all elements, integers related to 1. That is the equivalence class corresponding to 1. Equivalence class corresponding to. And these are the set of all integers related to 2. And this is equivalence class corresponding to 2. Equivalence class corresponding to 2. So, here comes the important result. Every equivalence relation defined on a set divides the set into pairwise disjoint equivalence classes or sets known as partition of the set. This is the important property of equivalence relation. So, if an equivalence relation is defined on a set, then that equivalence relation will partition that set into disjoint equivalence classes. Now, these are the things what we have to study in the relations. Thank you.